Hello everyone, welcome back. In this video, we'll be taking a look at the monotone convergence theorem. So before we go into the monotone convergence theorem, let's take a look at some definitions. So we say a sequence is increasing if an is less than or equal to an plus 1, i.e. the an plus 1, the succeeding term of the sequence, is less than the previous term, then a sequence is increasing. And we say a sequence is strictly increasing if an is less than an plus 1. And similarly, we say a sequence is decreasing if an is greater than the succeeding term, which is an plus 1. And we say a sequence is strictly decreasing if an is greater than and not greater than or equal to an plus 1. And if a sequence is both increasing or decreasing, if a sequence is increasing or decreasing, then we say the sequence is monotone. So a monotone sequence is a sequence which is either increasing or decreasing, or it can be both, or it can be strictly increasing or strictly decreasing. So the monotone convergence theorem, it states that if a sequence is monotone and it's bounded, then it converges. So let's do the proof of this. So remember that to show that a sequence converges, normally we were calculating the limit of the sequence to show that it converges to the particular limit. But from now on, we have another way to show convergence. All we need to show is that a sequence is bounded and it's monotone. If we show that a sequence is monotone and it's bounded, then it automatically converges. So let's do the proof of this theorem. So let an be monotone and bounded. So we now need to show that this sequence converges. To prove an converges using the definition of convergence, we're going to need a candidate limit. So let's now assume that the sequence is increasing and the case for the sequence is decreasing is handled similarly. And we consider the set of points an for n in the national number. Since it's bounded, all the sequence terms are within a particular set which is within this particular interval. It's bounded. Since the sequence is bounded, all the sequence terms are in this interval. And if you remember the axiom of completeness, it said that every non-empty bounded interval has a supremum. So we're going to use the axiom of completeness to prove this theorem. So the axiom of completeness said that every non-empty bounded interval has a supremum. So our sequence terms are in this interval, so it's non-empty, and we know it's bounded because we are assuming it's a bounded sequence. Therefore, it has a supremum. So the sequence an has a supremum s, which is equal to the s is the supremum of an for all n in the natural numbers. So let this supremum be our candidate limit. So we're going to say this sequence is converging. It's reasonable to claim that the limit of an is this supremum, is the s. So to prove this theorem, so let epsilon be greater than 0. Because s is the supremum, s is the least upper bound, s minus epsilon, since s is a least upper bound, remember, s is a least upper bound, so s minus epsilon, certainly s minus epsilon is not an upper bound, is not an upper bound, certainly there is some n, there is some I'm gonna write an which is greater than s minus epsilon. Remember, s is right here and s minus epsilon is right here. So there's some sequence terms which exist between these two. So I'm going to say an is greater than s minus epsilon. There's one an right here which is greater than s minus epsilon. And since this sequence is increasing, we are assuming the sequence is increasing, and the case for decreasing is done similarly. So an is greater than a capital N, and a capital N is greater than s minus epsilon. So let me write this here again like this, an, and we know that an, since the sequence is bounded, and it's bounded by the supremum, it's all the sequence terms are less than s, which is the supremum, which is our candidate limit, and this is less than, of course, s plus epsilon. So now we're nearly done with the proof. Now we're gonna deal with this, and this. We're gonna combine them to look something like this: s plus epsilon, s minus epsilon, and this is the same as an minus s being less than epsilon. And now we've shown that it converges, because we have taken s to be our candidate limit. Remember, from we have assumed the limit of an is equal to s, and we have now shown that it converges. So now we have proved that every sequence which is monotone and every sequence which is monotone and bounded certainly converges to some limit. And we're done with the proof. So hope you guys have enjoyed this video. See you next time.